Hello and welcome back to another great year of lesson 3.6. L 3.6 right here. All right, let's get into it. Claims and conjectures. So remember, conjecture is a mathematical idea that you think is true but don't have a proof for yet, but might be able to prove it and probably can prove it. So you created the following diagram previously by rotating a triangle about the midpoint of one of its sides. So remember back to this moment. We did this together. We traced this triangle. I don't know why I pronounced it like that. That seemed weird. And then we found the midpoint of the side, so the middle. So we rotated 180 and lined it back up. I mean, we wouldn't have to line it up if it was exactly 180 or if we had the exact middle. But you can cheat even if you don't have the middle because it's supposed to line back up with itself. Then you found the midpoint here, and then we rotated it around again. Beep, 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 beep. I should really pause it. That's a new year, and I haven't learned my lesson. Okay, something like that. And that is what this is. But because we were rotating the same triangle, we know this angle is the same as this angle. And this angle rotates down here. So these are all the same. And those two are the other two angles, and they're all there. And this is how we first really kind of demonstrated that all three angles of a triangle always add up to 180 because you can always get them together on a straight line like that. But today we are going to extend this diagram until it fills the paper. We also already did this. This type of plane filling diagram is called a tessellation. Tessellation from the Greek word for tile, tiling the plane. Think of a tile floor, or even the tiles in our school's hallway. Though that's a tessellation, very boring. All squares, but squares tessellate the plane. So cool. Okay, we already did this. Ruler, trace a triangle, build your tessellation. Here's some examples of some tessellations. Okay, this person used this triangle. This person used a slightly larger triangle. We'll come back to these in a second. Make a conjecture about vertical angles. Oh, remember vertical angles? Cha-cha. Where two straight lines cross. These are also vertical angles to each other. And something new, ding, 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 exterior angles. That is, when you have a triangle, this angle is exterior to the triangle. It's along one of the triangle's sides. But something interesting happens because this adds up to 180, but also inside the triangle adds up to 180, and ding ding, this little angle is part of both of those things, so we're going to be able to do some fun stuff there. Make conjectures about angles formed when a line intersects two or more parallel lines by reasoning with a diagram. We actually did a lot of this before break, so we are already masters of the parallel lines cut by a transversal situation. Oh, look at that. Tiling of the plane. The diagram from How Do You Know That has been extended by repeatedly rotating the image triangles around the midpoints of their sides to form a tessellation of the plane as shown. Using this diagram, we will make some conjectures about lines, angles, and triangles, and in the next task, write proofs to convince ourselves that our conjectures are always true. Or in these cases, true. First, we need to name and define some new angles that occur in this diagram. Read the descriptions of each of these angles as given in the task, and then record the definitions of these angles in your own words. Because we're such an awesome geometry class, we already know about these things. But I think coming back from break in the new year, it's nice to do a little review. So we're just reviewing. When two straight lines intersect, the adjacent angles form linear pairs of angles because they are supplementary angles. That is two angles whose measure sum to 180 degrees. What? When two straight lines intersect, the adjacent angles form linear pairs. Oh yeah, linear pairs. So they're saying these are a linear pair, these are a linear pair, these are a linear pair. Did I get them all? These are a linear pair. So lots of linear pairs. My goodness. But the opposite angles formed at the point of intersection are called vertical angles. There we go. The opposite ones are the vertical angles. In the diagram, angle 1 and angle 3 form a pair of vertical angles. What diagram? This diagram. 1 and 3, 2 and 4. 1 and 3 are vertical, 2 and 4 are vertical. Examine the tessellation diagram, looking for places where vertical angles occur. You may have to ignore some line segments and angles in order to focus on pairs of vertical angles. Yes, indeed. So how do we do that? On this diagram, let's look at an intersection here. These are angle 3s. Of the triangle has 3 angles. 3. So is this 2? 2, 3, 2, and 1. Okay. So at the intersection, you have 1, 2, 3, 1, 2, 3. But we don't want 6 angles at an intersection. We want only 2 angles. So the angles 1 makes the red angle, and 2 and 3 added together make blue. So this is the thing we're ignoring. So the reds are vertical, and the blues, which are made up of 2 corners of the original triangles, but we've squished them together to make a new mega angle called blue. And as you can see, oh, there's a blue in here, and down here along the transversal, because these are parallel, we have a blue. And vertical to the blue is a blue. Okay, and if we travel down the transversal to the next parallel line, in the same spot we have a blue. And opposite interior angle is the blue. This B should really be bigger. All right. My conjecture. You know what the conjecture is. We can actually prove it. Vertical angles are congruent. Oh my gosh. How about okay, here's something new. Exterior angles of a triangle. When a side of a triangle is extended in a straight line, as in this diagram, the supplementary angle formed on the exterior of the triangle is called an exterior angle. This thing, number 4. Ding ding. Cool. Coolness. What's going on with my camera? All right. Oh my gosh, it is bad. What is going on? Let's do bam, bam. Oh, that's zoom. That's what the problem is. I don't want zoom. I want brightness. There we go. My conjecture. Okay, this is kind of interesting. Note that the exterior angle and the adjacent interior angle form a linear pair. Yeah, we know that. The exterior angle and this adjacent interior angle. Adjacent because it's like next to it. Interior because it's like inside the triangle. Boop. And they make a linear pair. Yeah, they're on a line. Yep, we get it. We get it. Form a linear pair of angles. The 2 angles of the triangle that are not adjacent to that exterior angle are referred to as the remote interior angles. I don't know why I circled them. If I'm going to point at them anyway. I like to circle things. I'm going to include more sound effects this year in my videos. If you have any ideas for content, please let me know, and like and subscribe. Okay, I said it. All right. Are we done with this? Remote interior. In the diagram, number 4 is the exterior angle. 1 and 2 are the 2 remote interior angles, and 3 is the adjacent interior angle. Okay, here's my conjecture. The exterior angle is cool. No, don't write that. That's not a mathematical conjecture, that's an opinion. Okay. Well, it's a linear pair. That's not even a conjecture. What could we conject? Well, here's an interesting idea. This adds up to 180, and everything inside here adds up to 180. So maybe the 4 and the 3 add up to 1, 2, and 3. Let's just make a note over here. 1 plus 2 plus 3. These are angles. Okay, fine. I'll write it correctly. The measure of angle 1 plus the measure of angle 2 plus the measure of angle 3 equals the measure of angle 3 plus the measure of angle 4. Oh no! I got it. I got it in there. Sloppy in the new year. Shout out to Liz Sloppy. Period 1. Alright. Measure of angle 3 plus measure of angle 4 equals the measure of angle 1, 2, and 3 added up. Because they both equal 180. They both equal 180. This equals 180. Everything in here equals 180. So, I wish I would have done this better. So the measure of angle 3 plus the measure of angle 4 equals the measure of angle 1 plus the measure of angle 2 plus the measure of angle 3. Great. What if we subtract the measure of angle 3 from both sides doing some algebra? Now we have the measure of angle 4, which is the exterior angle, ding ding, equals, that's gone, so it's just these two, the measure of angle 1 plus the measure of angle 2, and that is these two. Look at that, 4 equals 1 and 2 added. That's not even a conjecture, we already proved it. Well, now you know the exterior angle theorem. That is the exterior angle theorem. And it's we just proved it basically. Remember, theorem means provable. We proved that. Now you know about exterior angles. Okay, parallel lines cut by a transversal. When a straight line intersects two or more other straight lines, the line is called a transversal line. When the other lines are parallel to each other, some special angle relationships are formed. To identify these relationships, we give names to particular pairs of angles formed when the lines are crossed or cut by a transversal. In the diagram below, 1 and 5 are called corresponding angles. 1 and 5, but also 2 and 6 are corresponding, 4 and 8. You guys know. You guys are good at corresponding. 3 and 6 are called alternate interior. 3 and 6. Because they're on alternating sides, but interior to the lines, the parallel lines. And 3 and 5 are called same side interior. Same side of the, and on the inside. Examine the tessellation diagram. Oops. So you'll notice same side interior are supplementary because a red plus a blue equals 180. But alternate interior, blue and blue, they're congruent. Looking for places where parallel lines are based on several examples of parallel lines and transversals on the diagram, write some conjectures about corresponding angles, alternate interior angles, and some side interior angles. Okay. First, corresponding. Now these are conjectures kind of so far because I'm not going to prove them right now, but maybe in the next task, next lesson. So those are corresponding. They're both red. They're both angle 1. So that's the symbol for parallel. Parallel. Corresponding angles for two parallel lines are cut by a transversal are congruent, alternate interior angles are congruent, same side interior angles are supplementary. I think we did it. Are we ready for more? I bet you are. Go ahead, try it. We just did the conjecture. I'm not sure why we need to do them again. I'm not gonna waste your time. I'll do this one. The exterior angle, the measure. How about that? Oh, I forgot the word angle. The exterior angle measure. Really, the word measure could go in front, but I forgot to write it, so I'm just doing it this way. The exterior angle measure is equal to the remote interior angle measures added together. Remember this? Remember this? I should get some colored pencils. Here's the exterior. These two is the same as this one. 3 is not involved. You can get 3 involved. Obviously, it was involved for the proof. But once you prove it, it doesn't matter. Those two add together, that one. If you know 4 and 2, you can figure out 1 by subtraction. All right. I'm not sure I was on the screen there. Must have bumped my camera. We'll do these vocabs on a separate vocab mission. Look at all that vocabulary. Let's retrieve. Diagram. Very fascinating. What do we notice? This segment is a radius of circle A and circle B. So circle A and B are the same. This segment from D to B is a radius of circle D and circle B. So those are, so we have 3 congruent circles. I wonder if I should switch over. Oh yeah. Oops. Great content. Segment AB is congruent to segment BD. Yeah. Oh, yeah. Congruent to DE, congruent to A. So, that. This box is irrelevant. Not applicable. Did we already do this? Yes. All AE, yes, all those segments are radii of congruent circles. So you don't even need to say they're saying provide a justification. They're not quite saying prove it. If we wanted to prove it, we could further say we know these are congruent circles because they share segments as radii. But they didn't even tell us like necessarily that B is the center of this circle, but we can assume it is the center for this little task. The point is, in your homework, you have similar stuff. You don't have to go prove everything. Just have an idea like, oh, that would be true because of this. And this is probably true. Just justify your thoughts. Is triangle BAE congruent to triangle BDE? First, let's find them. B, A, E. Whoa, it's the long one. B, D, B. Shared side. Yes. Side, 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 congruency. I'm not even going to write y. There's a shared side and then 2 radii, but we're just justifying here. Does angle EBD be congruent to angle EBA? Ooh, yep. CPCTC. Who remembers what that means? Corresponding parts of congruent triangles are congruent. We just proved that the triangles are congruent. Are those corresponding parts? EBD, EBA? EBD, EBA. Yeah, since the two triangles are, well, it's tricky because it's a isosceles triangle. It's isosceles because these two arms are the same, and the congruent triangle up here is also obviously also an isosceles. So really, what corresponds with what? Did this corner rotate over here, or did it reflect over? Isosceles triangles, there's actually 2 ways to correspond. These are corresponding in one interpretation of the 2 congruent triangles. So, because they're corresponding, those 2 angles are congruent. Because we already proved the triangles are congruent, CPCTC. Oh my goodness, absolute value functions. Did you study these? If you know how to do this, do this. If you don't, skip. Skip if never seen. If you kind of remember, the deal is that is an absolute value bracket, which means you evaluate inside the bracket, and then if it's negative, you take the positive value. If it's positive, you keep the positive value. The graphs end up looking like a V. And you can make a T-chart. And plot some points. And we're ready for the homework. Is there anything I need to say about this? Looking at this, can you prove that these angles are all right angles? Find those angles. And again, it doesn't have to be fancy. You're not totally proving it. You're just saying, yeah, they're right angles because I know that the relationship between these 2 lines is a certain relationship, which you can remember from your constructions. Enough hints. This one was challenging, but you can do it. What would you add to the diagram? Okay, sometimes when creating a proof, it is useful to add additional segments to a diagram. Amelia is conjecturing that segment EB is congruent to segment FD. Look at these. Here's EB, here's FD down here. These little guys. Gosh, we hardly know anything about those. Those are parts of 2 funny parts of a line. But she thinks they're the same. To prove this conjecture, Amelia thinks she will need to add to the diagram in figure 1. What would you add to the diagram? How might this addition of an auxiliary segment be used in the proof? So, you're trying to prove 2 things congruent. What sort of things do you already know are congruent? We've seen this diagram before. Could you add some more lines? Let me show you an example. Here's a line. Here's 2 new lines. I know they're congruent because they're both radii of circle A. Maybe you can add some radii. It gets kind of jumbled up in there. That's why I drew my examples off to the side. But anyway, add some lines, then say how you'd use them to prove that this little guy is congruent to this little guy. All right, make some conjectures since the set, based on the information in the statements or diagrams, it is possible to make claims about what is likely true. The claims are considered conjectures because they have not yet been proven or disproven. For each problem, use the diagram and statements to generate at least one conjecture about the quadrilateral. Attempt to conjecture about the most precise classification for the quadrilateral. Is it a square? Is it a rhombus? Is it a parallelogram? Just, if you're given that information, maybe mark it up, and then, based on the mark, say, I think it's a blank. Oh no. And then skip the go. Alright. 26 minutes. Well, Happy New Year's. Well, that was the lesson and the homework combined together. Alright, if you're watching this on Thursday, my birthday's tomorrow, but I will be here.